chapter 4. And by starting chapter 4, we are also starting a movement, an initiative, and y'all are part of it. We are starting the movement for anti-derivatives. Down with derivatives, right? We're going to pick it. We are against derivatives. Anti-derivatives. The future is now. And indefinite integration. How are we going to integrate? Indefinitely. That means forever and ambiguously, right? We don't know what we're doing, but we're going to do it forever. Indefinite integration. The federal government, right. Okay, so we're going backwards. We've learned how to go forwards, taking derivatives. An antiderivative is basically undoing a derivative, okay? And there'll be some rules for that, some of the things that we have to memorize. But if you've ever tried driving home after school, you know going backwards is always more fun than going forwards, right? You drive in reverse, you know, backing up a trailer, all that good stuff. So this will be fun, fun, okay? Fun. I'll add another one. Now, indefinite integration is another thing that's going to be synonymous with finding an antiderivative, which is called anti-differentiation. And there is later going to be something called a definite integral. So we'll compare it and contrast it, maybe write an essay about them, indefinite versus definite. Okay? So the first thing I want to do is suppose that we have a function capital F, all right? Capital F, whose derivative, big F prime, is defined to be little f, and that's going to be x squared. All right, so every time we take the derivative, we put a little prime. But if we're starting with this new function little f, and we don't call it f prime, we need some name to designate for some function that came before it. And so we usually use capital F. So if capital F then has a derivative whose x squared, can we become mathematical sleuths and figure out what big F of x could have been to start with, so that when we take the derivative of it, we get x squared? We can try. I like that. Like the Texans try to win a football game last Saturday. Whoa, ouch, right. Any ideas? Well, let's see. We use the power rule to get x squared, right? And every time we take the derivative, we multiply and subtract. So we know it had to start off as a what degree? An x. It had to be an x cubed, right? So you could do your what's called the guess, check, revise, and smile method. It's called the guess, check, revise, and smile method. So if our guess is x cubed, let's check. Okay, we're on the check now. Big F prime of x is going to be 3x squared. You compare that to what you want, and you're like, I'm so close. I just have this unwanted factor of 3, right? So now we can go back and revise, and you're like, self, I need to have something right there to intercept that unwanted factor of 3. It's like knowing you're going to go to the Mexican food restaurant, you're going to have a big old steamy plate of enchiladas, and knowing that in advance, you take some Prilosec before you go, right? Right? We're going to anticipate in the future having a 3, and so we are going to put what in front to neutralize that unwanted acid? A 1/3, right? Because anything times its reciprocal is what? 1. So now I have revised it, and I guess you can keep this going in an indefinite loop, right, until you get it right. Let's check it again. Let's check number 2. Big F prime of x is going to be, let's see, 3 times 1/3. Why, that's 1. No heartburn. X squared. That's what I want. And so now guess what? We're at the end of the process, which is smile. Of course, you're smiling all the way through because it is fun, 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 fun. All right. So we call 1/3 x cubed an antiderivative of x squared. Now, an, is that a definite article or an indefinite article? Bless you. It's a definite article. Well, it's definitely an indefinite article, for sure. Okay? Because an antiderivative as opposed to what? The antiderivative. That's a definite article. We only call it an antiderivative. Why? That kind of implies that there might be more. Really? More. Okay. Well, if there's more, then let's see if we can come up with another one. Big F of x, well, let's guess, check, revise. How about x to the fourth? Oh, that's not going to work. That's not going to work. I think this has got to be a 1/3 x cubed. Plus 5, you said. Will that work? Yeah, I believe so, because the derivative is going to be x squared plus 0. The derivative of 5 is 0. So there's another antiderivative. How about 15? Will that be another one? And 151, is that another one? Yeah, how many antiderivatives are there? Infinitely many. Yeah, infinitely many. But they all differ just by a what? By a constant, right? Because we know when we take the derivative, we lose information. So here we go. We can actually come up now with a general antiderivative. Squeeze that in there. A general antiderivative would be big F of x, and we could say it's 1/3 x cubed. And to represent any unknown constant, we typically use the capital letter C, and it's world-renowned. Plus C. The bane of calculus students. Wow, plus C. Don't forget plus C. I forgot something. I'm done. No, you're not. You didn't put plus C. Oh, plus C. Okay, plus a constant. Because what's the derivative of any constant? 0. All right. So there you go. Let's go ahead and define. A function big F is an antiderivative of little f on some interval if big F prime equals little f for all x in the interval. Okay. Now, when you look at these antiderivatives, the plus C, here's some examples, right? They have plus 3, plus 2, plus 1. What does this do? If I were to sketch the antiderivative, what does plus C do to all your graphs? Shifts them what? Vertically, up or down. So they're all going to differ by a constant, which means they all differ by vertical shift. So, for example, if you were looking at this particular value of x, let's call this x equals c, the slope of the tangent line is what the derivative function is going to give us. That would be the slope of that particular solution, okay? Once you have a value of c in place, we call these particular solutions, as opposed to, or particular antiderivatives, I should say. We haven't gotten to the solution part yet. Particular antiderivatives, as opposed to a general. If we did a vertical shift, notice what is going to happen with the tangent lines. Well, when they shift up vertically, the slope stays the same because all of these tangent lines are what to each other? A vertical shift doesn't affect the value of the derivative at a point because it keeps the tangent lines parallel to each other, right? That's what I was looking for, parallel. So a vertical shift doesn't affect the value of the derivative. They differ by a constant. It goes to 0. All right, that's pretty cool. Now, the guess, check, revise, smile method is not a bad thing, but, you know, guessing and checking is not always the most efficient method. So what we want to do is come up with some standards or some rules, some algorithms that we can do in general, and maybe even memorize a few common antiderivatives so we don't have to reinvent the wheel every time we want to ride a merry-go-round. Example 1. We're going to find the general antiderivatives of each of the following by using your knowledge of how to find derivatives. Okay. Now we're going to practice not just finding antiderivatives, we're going to practice our notation as well. Our notational location. Needs to be in the right spot. Okay. So, little f of x is equal to 2x. What would the antiderivative of little f be on the left? Big F, right? That's just the distinction that we give it, such that big F prime is little f. So we get big F over there, and the antiderivative of 2x. What do we take the derivative of to get 2x? X squared, and then, of course, we leave the allowance for any possible constant to be there by putting plus c. So that would be the general antiderivative. And if you check it, you can do it in your head, right? What's the derivative of x squared? 2x. Good. Smile. All right. Sweet. How about this one? On the left side, the antiderivative of little f prime. Well, every time we take the derivative, we add another prime notation. So every time we take an antiderivative, we take one away. So if I take away the prime, I'm left with what? Just f. You can think of that as the zeroth derivative, but we don't write the zero right there, but it's kind of like the zeroth derivative. It's the function. So the antiderivative of f prime is f. And what is the antiderivative of x? 1/2 x squared. You anticipated having the heartburn, so you took the antacid of 1/2 in front to neutralize the 2. You put a plus c there. Yeah, good. Excellent. All right, how about this one now? On the left side, the antiderivative of big F prime. Big F, good. Doesn't matter what the name is. If there's a prime there, you take one away. We could also, I guess, call the top function little f. That's what we defined big F prime to be. Okay, 2/3 x to the 4/7. Not quite as intuitive as this guy, right? Well, let's see. Let's see what we know about going forward. When we take the derivative using the power rule, it's of the form a times x to the n. We multiply first, right? A times n, and then we subtract 1 to get our new exponent. When we're doing the antiderivative then, we're not multiplying and subtracting. We're going in reverse, right? So if the last thing we did on the power rule when we took the derivative was subtract 1, the first thing we could do when we're finding the antiderivative is what? Add 1. So 4/7, when I add 1, gives me 11/7. Okay? That would be the exponent I started with. Now, if the first thing we did when we did the power rule on derivatives was multiply, then the second and last thing we'll do up here is not multiply, but divide. Yeah. And dividing by 11/7 is the same as the multiplying by 7/11. Yeah, so you can think about it another way. You can think about it as the heartburn case, right? We know we have an 11/7. When I take the derivative, it's going to become a factor here, and I want it to be gone so that I'm just left with the 2/3. So I know I want the 2/3 to be the final answer. I just need to have something in front of that x to neutralize the unwanted 11/7, which will be its reciprocal. Always its reciprocal, because anything times its reciprocal is what? 1. Yeah. So as we start going forward with antiderivatives, I tend to call this constant multiple 2/3, I tend to call him the rider. He's riding along through the problem. He's there in the beginning, he's there in the end, he's in the back of the truck. He doesn't even know what's going on, right? And then this 7/11, this is your antacid, this is your correction, right? It's your correction. Because you know when you take the derivative, you're going to be off by, you're going to have an unwanted 11/7, and you can neutralize it by putting a reciprocal of that unwanted number there. And then, of course, we don't forget, because it's easy to forget because it's so easy, we make the allowance for the general antiderivative to have any constant at the back end, so plus c. So what did we really do? We, instead of multiplying and subtract, we added 1 to get our new exponent, and then we just divided by the new exponent, or in this case, multiplied by its reciprocal. And once you have that, feel free then to tidy up the place a little bit. Combine your two numbers that are there in front. I don't think anything divides out, so we end up with the wonderful number 14/33 x to the 11/7 plus c. And we have now made a systematic process out of finding the antiderivative rather than just saying, oh, 2/3 x to the 4/7 of, I don't know. Okay? Whatever's there in the beginning, the 2/3 stays put, and we put the reciprocal of that new exponent in front. So we added and divided. Let's see if it works. Working backwards now, just to see. That was a 1x to the first. So let's see. If I add 1 to 1, I get 2. And then dividing by 2 is the same as multiplying by 1/2. It works. This is 2x to the first. I add 1 to get my new exponent of 2. And then I divide by my new exponent 2. 2/2 gives me 1. It works. Add and divide. It works. That right there is called the power rule. So let's go ahead and do that. If f prime of x equals a times x to the nth power, then f of x is going to equal a times 1 over n plus 1 times x to the n plus first power. And then, of course, what? Plus a constant. Yeah. So essentially, we're adding 1 to n to get our new exponent n plus 1. And you could either divide it by the new exponent or put the reciprocal in front. We can, I guess, call that the power rule for anti-differentiation. It's kind of like when we find inverse functions, we do the inverse operation in the reverse order. We're doing the same thing here. We're adding and dividing instead of multiplying and then subtracting. Okay, so that makes it easy. So now we can do something like this. G prime is equal to 1 over x squared. What? Negative 1 over x? Yeah. Yeah. If we're going to use the power rule, just like taking the derivative, we would need to be able to write it in that format, yeah? So in this case, I would have to rewrite it if you were going to show the steps. You'd have to bring the x to the top, and it would be 1 times x to the negative second. So now it's written in the power rule format. Now we can take the antiderivative. What becomes of the left side, the easy side? Just g of x, good. And now by the power rule, we will add 1. So negative 2 plus 1 becomes negative 1. And then, of course, we divide by the new exponent, but dividing by negative 1 is the same as multiplying by negative 1. And right there is where you need to put your plus c. If you plan on simplifying your expression, you still need the plus c right there as soon as you take the antiderivative. And then, of course, if you want to clean that back up, that's the same as negative 1 over x plus c. Very good. Guess, check, revise. You're going to get to the point where you don't even really need to check unless it's just like mentally. But if you're ever in doubt of whether you have the right antiderivative, that's what's so cool about it. You can check, right? Because you take the derivative, compare it to what you started with, and if you're off, you can tweak it and revise it. You can check your work now because you know how to take the derivative. Okay, over here, dy dx. What becomes of the left side when you take the antiderivative? Y. That's Leibniz notation. So over here, we use the power rule, right? That's cosine to the first, so it becomes cosine squared divided by 2 or times 1/2 plus c. Is that right? Well, I don't know. Let me check, right? Guess, check, revise. I got the left side correct because when I take the derivative of y, I get dy dx. Now on the right side, I guess I'd have to use the chain rule. 2 times 1/2 is 1. Times cosine of x to the first, times the derivative of cosine, which is negative sine of x, and then, of course, c goes to 0. Oh, boy, that's not right at all. That's not right at all. Okay, time to revise. I got too much trig right there. Too much trig. So the power rule doesn't always work, does it? Sometimes it's just as simple as saying the derivative of what equals cosine? Not sine or negative sine? Yeah. It could be a guess, check, revise, and smile. What would be the derivative of negative sine? Negative cosine. So, with the negative would be gone. Yeah, that's what's awesome about anti-differentiation. You could actually check, take the derivative. So the derivative, the antiderivative of cosine is sine. Now, since we're right here, what would the antiderivative of sine of x be? Very good. You might guess cosine plus c, but then the derivative of cosine is negative sine, generating an unwanted negative. So how do you neutralize an unwanted negative? You just have a negative 1 factor in front to intercept it. Yeah. So the antiderivative of sine is negative cosine. Guess, check, revise, smile. Easy. Okay, so here are some basic properties of antiderivatives and some rules all in one. If you have a constant multiple times a function and you're trying to find its antiderivative, that's what I call the rider. He's there in the beginning, he's there in the end, he goes along for the ride. He doesn't even have to be part of the process of antidifferentiation. Just let them hang out front and multiply them by your final answer. Once you find the antiderivative big F, multiply any constants together up front. Just like when we're taking the derivatives, if we have multiple terms, whether they're added or subtracted, you can think of those as miniature problems. And you could just focus on each term one at a time, take their antiderivatives, and then add them together, of course, putting plus c at the end. This next one is the power rule, and I left the coefficient off, but if you have something of x to the nth power, then it becomes x to the n plus 1, and then, of course, you either divide by n plus 1 or multiply by its reciprocal plus c. That's the power rule right there. That's the power rule. But it does have one limitation, and that's this right here. It says when n isn't negative 1. Let's see why. Right here, let's squeeze it in here. What if I have dy dx equaling x to the negative first? Well, the left side becomes y, and if I try to use the power rule, what does the power rule say? I add 1 to negative 1 to get 0, and then I multiply by the reciprocal of 0 or divide by 0, not forgetting to put plus c. Whoa, whoa, what just happened? We divided by 0. Is that legal? Are we Newton? No. Are we Chuck Norris? No, we're neither. So we can't divide by 0. So that doesn't work. So the power rule fails every single time your exponent is negative 1. Does that mean it can't be done? It can't be done using the power rule. But if you just kind of reframe the question, x to the negative first is also called 1 over x, right? And sometimes a simple question like, what do you take the derivative of to get 1 over x, could be a very successful way to find an antiderivative. Yeah, because that would be the natural log of x. Very good. Now, here's the thing. We always want to keep the domain, if we can, of what we started with. So in this case, if we're starting with 1 over x, what's the domain of 1 over x? Everything except 0, right? Including negative numbers. If I take the antiderivative and get natural log of x, and I leave it like that, now x can only be what type of number? Positive. It still can't be 0. That's good. Natural log of 0 is undefined, but I want to be able to include negative numbers in there. So guess what I do? I throw that on there, and now that allows positive numbers, and of course I put plus c. And if you want to check, right, let's check. What's the derivative of the natural log of the absolute value of x? How do the absolute values around the argument affect the derivative of the log? They don't, right? We showed that 2 different ways, piecewise function and graphically. So they'll go away, and you just get 1 over x, and then, of course, c goes to 0. So there's a rule. You can think of that as a rule if you want. Here's the summary of it. The antiderivative of 1 over x, or x to the negative first, is the natural log of the absolute value of x. And when you think you're done, put plus c and then walk away. Golden Gophers, -3 degrees yesterday at kickoff. Did you watch the game? You watched part of it. It was the 3rd coldest playoff game in NFL history. Yeah. Brrr. Okay. Yeah. Brrr. All right, cool. Anyway, let's do this one. E to the x. E to the x. What's the antiderivative of e to the x? Very good. E to the x plus c. I'm glad you didn't forget the plus c. And, of course, if you check it and revise, there'll be no revision. All right, good. All right, what's the antiderivative of cosine then? Just to have them together, the antiderivative of cosine. What do you take the derivative of to get cosine? Sine of x plus c. So we're thinking backwards now, right? So remember, when you take the derivative of anything that starts with co, you get a negative. But the antiderivative of cosine is positive sine. What's the antiderivative of positive sine? We already said was negative cosine. And that negative is there as a correction, because when we take the derivative, we generate an unwanted negative. How about secant squared? What's the antiderivative of secant squared? Tangent of x plus c, right? So all the derivatives that you memorized, if you just flip them around, you have some antiderivatives memorized. Let's see, next column. What would be the antiderivative of cosecant squared? Cotangent? Guess, check, revise, smile. Negative cotangent of x plus c. Very good. Negative cotangent of x plus c. Again, the negative's there as a correction because the derivative of cotangent will generate a negative cosecant squared. And so there's the antacid. All right, the antiderivative of secant tangent is secant of x plus c. Yeah, very good. The antiderivative of cosecant cotangent period. Oh, I have a period there. Yeah, 0.00 trailing zeros. What's the antiderivative of cosecant cotangent? Negative cosecant of x plus c. Again, a correction, right, of an unwanted negative. How about this? What's the antiderivative of 1 over square root of 1 minus x squared? Arc or inverse, like a snake, sine. Inverse sine of x plus c. All right, all those derivative rules, we got to know them. What's the antiderivative of 1 over 1 plus x squared? Arctangent of x plus c. Arctangent of x or inverse tangent of x plus c. And then this dude, 1 over x squared of x squared minus 1. Arc or inverse secant. Yeah, now this one is interesting. Remember when we take the derivative, we add absolute values around that x right there. Okay? But if we start with that and the absolute values aren't there, we add them right here. Okay? So there's that one little thing. The arc secant is always kind of high maintenance, if you will. Add the absolute values. Good. So if you think you need to go back and brush up on all your kind of derivative rules, they should help you moving forward with your antiderivatives. And we're on assembly schedule here today, so we're in here until 11:55. So announcements should be coming on soon. All right, ready for example 2? I am. Boy, howdy am I. Find all functions g such that g prime is equal to that. Find all the functions in the whole wide world so that when I take the derivative of them, I get this. Okay, well, sometimes we need to rewrite before we jump in and start working, correct? And you want to make sure that your notation is always spot on. So unless you're going to take the antiderivative of both sides completely, I would say rewrite it first completely and then integrate, or I'm sorry, anti-differentiate all at the same time. All right, so let's look at the terms. 4 sine of x, there's the first term. That one looks pretty easy. The 4 is your constant multiple. He's the writer. He's there in the beginning. He'll be there in the end. But notice up here, I have a quotient. And just when we had the power rule for derivatives, same thing here, I can't just take the antiderivative of the top and the antiderivative of the bottom. There's no quotient rule like that. So I need to be able to split that up into individual terms, right? And we know how to do that. So we can split that up, just thinking. Same thing over here. We have 3 terms in the top and 1 in the bottom. I'm going to have to split that one up as well. So we got a little bit of housekeeping before we can go to the antiderivative. So we're still calling it g prime. The first term looks good. Here we go. We'll do this in one fell swoop. 2x to the 4th over x simplifies to 2x cubed. Minus, that's really x to the 1/2. So if I subtract exponents, I get 1/2 minus 1. That's x to the negative 1/2. You want to bring them to the top. So instead of leaving a residual radical in the bottom, we'll leave a negative radical in the top. And then I get x plus x, or x over x, which is plus 1. That takes care of that one. Now the second one's going to be just as fun, but with one little caveat, right? What's out front of there? A negative. And that's kind of important. That's going to change all the signs as well. So I'm going to have a minus. Your x's will divide out, leaving just a 7 cosecant squared of x. And then here's the one that maybe you might miss, minus 1 over x. And of course, you can leave it as 1 over x, or you can write it as x to the negative first. All right, I think we're ready to go. Let's do it. Don't forget the all-important left side. What's the antiderivative of g prime? G. Okay, and then over here, the antiderivative of 4 sine of x. Again, if you think it's just 4 cosine of x, that's your guess. You check it. The derivative of 4 cosine is negative 4 sine. You're like, ooh, need to revise. I need a negative in front there to neutralize the unwanted negative. All right, this one, you could do it in your head, right? It's the power rule. The 2 is going to go along for the ride, but really we add 1 to get 4. So you know you're going to have x to the 4th. And then you divide by 4, multiply by a 4th. Now you can incorporate it immediately with the 2 if you want to, right? 2 times the 4th would give you 1/2. So add and divide. Add and divide. 3 plus 1 is 4. Divided by 4, you get 2/4 is 1/2. Minus. Leave a little space here. I like to leave a little space in the front because that's how we do the power rule. X to the negative 1/2. When you add 1 now, because we're going backwards, what's negative 1/2 plus 1? 1/2. Good. So now the rule says you divide by 1/2, which is the same as multiplying by its reciprocal, 2. And you put it in that little space that you left. And a very quick check, negative 2x to the 1/2, when you take the derivative, you get 1/2 times 2, which is 1. Boom. 1/2 minus 1 is negative 1/2. Guess, check, revise, smile. All right, the antiderivative of 1. X, right? X. What's the derivative of x? 1. What's the antiderivative of 1? X. Cool. Minus, I guess 7 goes along for the ride, constant multiple. Cosecant squared. What's the antiderivative of cosecant squared? Tangent or cotangent? Cotangent of x, right? But then you check, the derivative of cotangent will generate a negative, which now will make that positive, and I don't want it positive, so again I have to have another negative correction, which now makes the antiderivative positive, yes? The derivative of cotangent now will turn that to a negative 7 cosecant squared. And if you had written the last term as x to the negative first, you might have tried the power rule, yeah? But as soon as you divide by 0, you're like, oh, yeah, can't do that. Natural log to the rescue, yeah? So minus the natural log of, absolutely, the absolute value of x. And then, of course, this is where students kind of walk away and lose points, right? Don't be a statistic, okay? Many students lose hundreds of points every year for forgetting the plus c when they're doing antiderivatives. Okay, so there it is. And, of course, we could go through and, well, maybe clean it up a little bit, but that's good right there. So a little bit of work on the front side, a little bit of preparation, and then term, boom, 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 down the line. Piece of cake. Now, is that all of them? It said to find all of them. Is that all of them, or is that just one of them? Yes, this right here, the plus c, makes it the general solution, or the general antiderivative, which means all solutions. Now you can pick your favorite value of c, add it on the end, and you have your answer. So most of the time you finish good things, and there's some little thing you do at the end, which is the cherry on top, right? When you do anti-differentiation, you don't have a cherry on top, you have a cherry off to the side, right? A little cherry off to the side with a black stem. Yeah, there's cherry. I'm an artist, not really. Okay, plus c. Don't forget your plus c. All right, so definition here. We got about 5 minutes. We know what an antiderivative is, right? The process of finding an antiderivative is called anti-differentiation. Here's another definition. A differential equation is an equation, surprise, surprise, that has a derivative in it. Okay? So, is this a differential equation? I see an equal sign. There's two expressions, one on the left, one on the right. Is there a derivative in it? Yes, there is. That's a differential equation. Okay? They get more elaborate than that. But a differential equation is basically an equation that has a derivative in it. You might be asked to solve a differential equation. Solving a differential equation means getting back to the original function from which the derivative came. So, for instance, if I gave you this and I said to solve it, well, if that's g prime, then solving it means getting back to g, the original function. Okay, and that's why I was mistakenly calling it the general solution before I'd given you that terminology. It's the general antiderivative, but now it's also the general solution to the differential equation. All right. The general solution, as we just saw, involves being the plus c, because that works in general for all different values of c. And as I mentioned earlier, having a particular antiderivative or a particular solution is going to require you to come up with a specific value of c. Now, in order to have a specific value of c, you need some information about the solution you're trying to achieve. So it's going to require essentially what's called an initial condition. And what is an initial condition usually? It's just an ordered pair. It's an ordered pair that satisfies the equation. Because remember, anytime you take the derivative, you lose some information. And so someone would have to give you a piece of information to help you kind of find it. And if an ordered pair is all you need, because if you think about this right here, the general solution, it's like a formula with three unknowns, right? You have your g of x, which is your y value. You, of course, have your x, and then you have your c, which is your third unknown. And if you know a particular x and y that satisfy the equation, you can plug it in for x, you can plug it in for y, and you can solve for c. And then once you have your c, you can rewrite the general solution with the value that you want. All right, very quickly, let's do example 3, and then we'll call it a day. Solve the differential equation f prime equals 3x squared plus 1 if f of 2 equals negative 3. There you go. F of 2 equals negative 3. That's some information about f, and it's an ordered pair. If you want to think about it like this, it's 2 comma 3. So my antiderivative of f prime, namely f, has to pass through that ordered pair. So that's going to come into play at the end. You don't do that until after you get the general solution. So that's what we do first. Number 1, find the general solution. And don't forget, you have two sides of the equation. So what's the antiderivative of f prime? F. And then over here we have two terms. 3x squared becomes x cubed, right? Add 1 and divide. Plus 1 becomes x, and then plus c. So there's the general solution. And again, if you want to check it quickly, take the derivative, you should get f prime equals 3x squared plus 1. All right, part 2, you're going to find c using what we are calling the initial condition. And again, you want to kind of show that you're doing that. So say, you could say when f of 2 equals negative 3. Or you could say at the point 2 comma negative 3, however you want to do it. We plug it in and we get negative 3 equals, plugging in a 2, we get 2 cubed, which is 8, plus 2 plus c. So negative 3 equals 10 plus c, and c equals negative 13. The final step is to rewrite your general solution with the c value that you found. So, it's a good transition word. F of x is going to equal x cubed plus x and then minus 13. And so there is the function f of x whose derivative is 3x squared plus 1. That happens to pass through the ordered pair 2 comma negative 3. Perfect. Yeah, great place to stop. The bell might be ringing shortly. So tomorrow we'll have that little quiz over related rates. I will not give you the formula for a cone or the color of the cone because that's going to be irrelevant. But the first one you need to know. You want me to ask you about the surface area of the cone? Have a good day.